Okay, so in this part of the video, I'm just going to give a brief introduction to London dispersion forces and permanent dipole interactions, and hopefully what I'm going to say will complement the notes and help you to answer the questions in the notes along with the information that's already there. So first of all, London dispersion forces, we did cover these in topic 1, so I'm going to just do a really brief recap. London dispersion forces, I suppose the word dispersion, so not that obvious where that comes from. To me, I think of it as in, it makes me think of the dispersion of electrons, how they are distributed around a molecule. So London dispersion forces happen when we have electrons, and the electrons are in the space around the two positive nuclei of the atoms in the molecule, and they're buzzing around the nuclei, doing their own thing, and we can imagine what we call an electron cloud around the atoms of the molecule. What can happen is sometimes the electrons are all moving quite quickly, and sometimes what can happen is we get a slight wobble in the electron cloud. We might end up at some random point with more of the electrons in the molecule over at one side of the molecule than the other. We know that electrons are negative, so if we end up with more electrons in one place than in another place where there's still equal numbers of protons in both sides, we're going to end up with a slightly negative part of the molecule and a slightly positive part of the molecule. So that wobble in the electron cloud leads to a separation of charge. That's what we call a dipole. And because it's just a wobble, it's a temporary dipole. It's a temporary separation of charge leading to a slightly negative, so that's the delta minus, and a slightly positive part of the molecule. What can then happen is if we have another molecule nearby, because the electrons in this one have wobbled and we've got a negative part of this molecule, well, the negative part of this molecule, remember, like charges repel. So if we've got more negative on this side of this molecule, that's going to repel the electrons away from the next door molecule. We're then going to end up with a slightly positive bit on the next door molecule, next to the negative bit on the original molecule, and then a negative bit on the far side of the neighbouring molecule. This separation of charges, which is caused by the original temporary dipole, is called an induced dipole. Now, this is all very complicated. The main thing you need to remember is that London dispersion forces arise from a wobble in electron clouds. I think that's the best way to remember it. And I also like to think of the electron clouds as a jelly, which you may remember in my previous video. So you can just think of it as a wobble in a jelly. The bit with the jelly wobbling towards it is going to be the slightly negative bit. So that's the key thing to remember. Don't worry too much about drawing these diagrams. You might get asked it. I think it's fairly unlikely though. So London dispersion forces, like I say, because they result in this wobble in electrons, basically they can happen in any substance that has electrons. So I suppose it technically applies to all substances, but particularly these are important forces in molecular substances, and they're found in all molecular substances. One thing that will become apparent when we look at the other types is that London dispersion forces are the only type of intermolecular force in non-polar substances. Now, because London dispersion forces are a result of these temporary wobbles in electron clouds, they are a relatively weak form of intermolecular force, particularly when we have small molecules. So small molecular substances like oxygen and nitrogen, they're just diatomics made from fairly small molecules. Small molecular substances which are non-polar, so diatomics would be a good example, only contain London dispersion forces as their main intermolecular force. And because these are quite a relatively weak type of intermolecular force, that explains why these small molecular substances tend to be gases at room temperature. Methane would be another really good example of a small molecular substance which is non-polar and therefore only contains London dispersion forces. So for small molecules, London dispersion forces are pretty weak, and that's why most small molecules that are non-polar are gases at room temperature. But what we've got to remember is that the strength of these intermolecular forces, these London dispersion forces, increases as the number of electrons in a molecule increases. Now, we don't always want to go down the line of counting exactly the number of electrons. You could do that by just adding together the atomic numbers of all the atoms in the molecule, but that's not always necessary. Generally, what you can do is, it'll be pretty obvious which has more electrons just by looking at the size of the molecule, but you can count electrons if you want. So a really nice illustration of this trend, this fact that the strength of London dispersion forces increases as the number of electrons in a molecule increases, is in the halogens. So the halogens are an example of non-polar substances. Both atoms in molecules which make up the halogens would be the same, so they would have the same electronegativity, equal sharing of electrons, and therefore be non-polar. So in the halogens, London dispersion forces are the only type of intermolecular force, but as we know from our previous topic, the size and the number of electrons within these molecules of the halogens increases as we go down the group. So fluorine is a very small molecule with a small number of electrons. Iodine is a much larger diatomic molecule with a very much larger number of electrons. So as we go down the group, we've got more electrons, therefore stronger London dispersion forces. And this explains why fluorine and chlorine are gases at room temperature, because they have the weakest London dispersion forces, the weakest intermolecular forces, and these forces therefore require least energy to break. But as we go down the group, bromine is a liquid at room temperature. It's one of the only liquids in the periodic table at room temperature, the only substances in the periodic table which are liquid at room temperature. And then finally, iodine is a solid at room temperature. So that's a really good illustration of this fact here. The strength of London dispersion forces increases as the number of electrons increases. And the fact that iodine is a solid at room temperature shows that when we do have bigger molecules, even if they only have London dispersion forces, they can still be solid at room temperature. So London dispersion forces, whilst they are fairly weak, they can be reasonably strong in large molecules, causing them to be solid at room temperature. Another good example of that would be wax, which is a hydrocarbon, non-polar, and only contains London dispersion forces. But because wax is really, really long hydrocarbon molecules, there's a lot of electrons per molecule, and it's quite a high melting point. Relatively high. So we learned about this factor already, but I'm just wanting to emphasise it. Another thing that you should be aware of when it comes up a bit more in Unit 2 is that the shape of the molecule also affects the strength of London dispersion forces. So there is an example of that in the booklet. I just want to sort of illustrate it again here. So if you've got a molecule that is quite linear, quite straight in structure, that means that it can sit quite closely together with other molecules. What that means is that there's a lot of surface contact between the different molecules. They can get really close to each other, and because London dispersion forces are an electrostatic force, the closer the molecules can get to each other, the better they pack together, the stronger the stronger the London dispersion forces can be between them. If, on the other hand, we've got molecules with a sort of strange, awkward shape that aren't going to pack nice and neatly together, you can imagine Tetris, this one's going to be a lot more awkward than this one. If the molecules are not going to be able to pack together as closely, that's going to mean that London dispersion forces cannot exist as strongly. There's weaker London dispersion forces between molecules of that are sort of an awkward shape that don't pack well together. So that covers London dispersion forces. Permanent dipole interactions then. So what we learned in the previous topic was all about polar molecules. So we were learning how to tell whether a molecule was going to be polar or non-polar. The reason this is so important is because molecules that are polar, as well as containing London dispersion forces, because remember all molecules or all substances contain London dispersion forces between the molecules. Substances which are made of polar molecules, we can call them polar substances, also contain these things called permanent dipole interactions. So when we have a difference in electronegativity, which leads to bond dipoles, and then also a non-symmetrical molecule, which leads to a polar molecule, what we end up with is what we call these permanent dipoles within the molecule. So in the molecule of hydrogen chloride, the hydrogen is going to be permanently slightly positively charged. The chlorine atom is going to be permanently slightly negatively charged. What that means is that if we've got two hydrogen and chloride molecules floating around, the negative chlorine atoms will be attracted to the positive hydrogen atoms in a different molecule. So you can think of it a bit like two magnets. If you've got some magnets floating around, then they'll be attracted, the opposite poles of the magnet or the opposite charged parts of the molecule will be attracted. So to represent permanent dipole interactions, we can just draw a dotted line. And the dotted line must always go from the negative part of one molecule to a positive part of a different molecule. It's really important that you don't get mixed up and think of these as attractions within a molecule. It's always between one molecule and another one. So if you're trying to represent intermolecular forces, you always have to draw at least two molecules. So, because these dipoles in polar molecules are permanent, this is a stronger type of intermolecular force than London dispersion forces. At least, and that applies at least as long as the molecules that we're comparing have similar numbers of electrons. So permanent dipole interactions are stronger than London dispersion forces if the number of electrons in the different molecules is similar. I guess one way of illustrating that is that this molecule here, so this substance here, hydrogen chloride, this is actually still a gas at room temperature, even though it does have these stronger permanent dipole interactions. Whereas wax, like I was talking about, this is a big, long, non-polar hydrocarbon molecule. It has quite strong London dispersion forces. It's a solid at room temperature. So if you're wanting to compare the relative strength of London dispersion forces to permanent dipole interactions, it's important that you compare molecules of a similar size and shape so that the London dispersion forces are similar.